Hello students, welcome to EPG Pathshala. I am Sumalay Roy from Department of Physics and Astrophysics of University of Delhi. Today we are going to discuss about module which discusses origin of quantum mechanics, that is part 1 from the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. How Planck proposed his idea of quantization of energy from the study of spectral distribution of blackbody radiation. 1. 2. Know Einstein's extension of Planck's hypothesis to resolve the paradox of the behavior of specific heat of solids at very low temperatures. 3. Study Einstein's generalization of photon picture of light to explain photoelectric effect. 4. Learn how to deduce the expression for shift in wavelength in Compton scattering of hard X-rays by elements of low atomic number. Quantum mechanics is considered as the fundamental theory describing the phenomena of molecules, atoms, and subatomic particles of matter. This subject evolved as a result of striking observation from number of experimental investigations carried out in different areas of physics from the end of 19th century to the beginning of 20th century. These observations could not be adequately explained on the basis of classical laws of physics. Historically, by the end of 19th century, classical mechanics as formulated by Newton and later developed by Hamilton and Lagrange was widely believed and universally accepted as the ultimate theory of dynamics. Similar was the status regarding the wave nature of light as established from the experiments on interference, diffraction, and polarization, and later developed in the form of electromagnetic theory of light by Clerk Maxwell and confirmed by Hodge in 1887 as electromagnetic waves produced by oscillating electric charges. However, by the end of 19th century, these classical theories were found inadequate to explain a growing number of atomic phenomena. Attempts were being made to explore the structure of matter and the nature of radiation and the interaction of radiation with matter. As a result, the first quarter of the 20th century witnessed how the foundation of physics were radically re-examined. In the present module, we shall trace the history of some prominent phenomena which point out the limitations of the laws of classical mechanics when used to study microscopic phenomena in physics, and show how these were overcome by Planck, Einstein, and Bohr, and later by Schrödinger and others. Prominent phenomena laying the foundations of quantum mechanics. Energy spectrum in blackbody radiation. One of the earliest phenomena for which classical theory was unable to offer any satisfactory explanation till the end of 19th century was the nature of the continuous spectrum of blackbody radiation. We all know that when an object is heated up sufficiently so that it gets red hot, it emits light at the red end of the spectrum. Further heating it causes the color of the emitted light to change towards shorter wavelength or higher frequencies. Recall that the black body by definition is one of which absorbs all the electromagnetic radiations which is incident on it and reflects none. Such a body is a better radiator at every frequency than any other at the same temperature. A perfect black body does not exist. However, for practical purposes, a black body is realized by creating a small hole in the wall of the cavity in which radiation is admitted from outside. The cavity contains radiations which is emitted by the walls of the cavity. The amount of radiant energy in the cavity does not increase indefinitely with time. In fact, the process of emission is opposed by the process of absorption. In the state of thermodynamic equilibrium, the amount of energy E nu d nu is the frequency range between nu and nu plus d nu is determined by the condition at which the rate of emission is balanced by the rate of absorption for a given frequency. It has been demonstrated both experimentally and theoretically that at equilibrium, the intensity distribution I nu, which is equal to Cu upon 4 pi into E nu, depends only on the temperature of the walls and is independent of the material of the black body, as shown in figure 1.1. So figure 1.1 shows a plot of intensity distribution as a function of wavelength lambda plotted at different temperatures. The figure clearly depicts this intensity distribution first rises to a maximum and then falls off as the wavelength increased. Maximum of the distribution curves slightly shifting towards the lower end of the wavelength as temperature increases. The observations could not be completely accounted for by the attempts based on classical ideas. Classically, the absorption and emission of radiation was considered to be due to oscillating charges within the black body. It was assumed that in a black body there are a large number of linear harmonic oscillators of all possible frequencies in equilibrium with radiation at a given temperature. Based on this consideration, while Wien suggested a semi-empirical theory which agreed only in the short wavelength limit, Rayleigh and Jeans, on the other hand, obtained a law which agreed at long wavelength limit but was in completely disagreement for short wavelengths. Thus, according to classical electromagnetic theory, the expression for the energy density distribution E nu of a black body radiation can be expressed as E nu equals to 8 pi nu square by c cube into U nu, where 8 pi nu square by c cube is the number of electromagnetic oscillators per unit volume at frequency nu in the range d nu in equilibrium with the radiation in a black body cavity, and U nu represents the average energy of the oscillators. By law of equipartition of energy, the mean energy of the oscillators with frequency nu is U nu equals to kT, where k is the Boltzmann's constant and T is the absolute temperature. Thus we get E nu d nu equals to 8 pi nu square upon c cube into kT d nu, or E lambda d lambda equals to 8 pi by lambda to the power 4 kT d lambda. This is known as Rayleigh-Jeans law, according to which the energy radiated in a given wavelength range d lambda decreases with lambda but increases with frequency indefinitely. This is depicted on the right hand side of the plot. For comparison, it also becomes clear from the above expression that the total energy E becomes E equals to 0 to integration 0 to infinity E nu d nu equals to 8 pi by c cube into kT integral 0 to infinity nu square d nu, which goes to infinity as nu approaches infinite. This basic drawback in classical theory is often referred to as ultraviolet catastrophe. Now, to obtain Planck's expression for the intensity distribution, we start by writing the mean energy per oscillator of frequency nu as U nu sum over n equals to 0 to infinity epsilon n n nu, where n nu is the number of oscillators with energy epsilon n in equilibrium with temperature T, given by the classical Boltzmann expression, which n nu equals to exponential minus epsilon n by kT divided by sum over n equals to 0 to infinity exponential minus epsilon n by kT. Substituting this expression in the above equation for U, we have U nu equal to sum over n equals to 0 to infinity E n epsilon n exponential minus epsilon n by kT divided by sum over n equals to 0 to infinity exponential minus epsilon n by kT. Now note that sum over n equals to 0 to infinity exponential minus epsilon n by kT is equal to 1 plus exponential minus h nu by kT plus exponential minus 2h nu by kT plus continuation dot 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 other terms. That is equal to 1 minus exponential minus h nu by kT to the power minus 1. Similarly, we can show that sum over n equals to 0 to infinity epsilon n exponential minus epsilon n by kT equals to h nu exponential minus h nu by kT divided by 1 minus exponential minus h nu by kT whole square. Thus, the expression for the mean energy per oscillators of frequency nu reduces to u nu equals to h nu exponential minus h nu by kt by 1 minus exponential minus h nu by kt equals to h nu by exponential h nu by kt minus 1. And the number of oscillators per unit volume n nu being equal to 8 pi nu square by c cube, we finally get Planck's revolutionary idea. In 1900, Planck put forth the idea that matter absorbs or emits radiation energy not continuously but rather in discrete quanta, assuming, as in classical theory, that a black body is composed of oscillators in equilibrium with the radiation field. He postulated that an oscillator with frequency nu can only take discrete values of energy quanta, which is given by epsilon n equals to n h nu, where n is 0, 1, 2 integral number as such, and h is a constant which is now known as Planck's constant, having value of 6.63 into 10 to the minus 34 joules second. Planck's expression for the energy density of radiation E nu 8 pi nu square pi c cube into h nu divided by exponential h nu by kt minus 1. This expression not only explains the observed spectral distribution of a black body but can also reproduce in the limiting case of Rayleigh-Jeans law. One can also show that the well-known Stefan's law can also be obtained from these general results. Thus, for example, in the low frequency or long wavelength limit, we can write e to the power h nu by kt nearly equals to 1 plus h nu by kt. Substituting this in the above expression, Planck's results reduces to Rayleigh-Jeans expression. Also, the total radiation density arising from all frequencies can be obtained by integrating Planck's energy distribution, that is E equals to 0 to infinity E nu d nu integral equals to 8 by 15 pi to the power 5 k to the power 4 by c cube h cube into t to the power 4, which shows that the energy density is proportional to the fourth power of absolute temperature T. This is the result which was first suggested by Stefan in 1879 and is known as Stefan's law of radiation. It may be remarked here that for quantum effects to show on observed temperature, observable departure from the mean energy U nu from its classical value kT. Note here that from classical consideration, Boltzmann expression is U nu integration over 0 to infinity epsilon exponential minus beta epsilon dE by 0 to infinity exponential minus beta epsilon dE equals to minus d d beta integral over 0 to infinity exponential minus beta epsilon into d epsilon equals to 1 by beta equals to kt. Reduces to this expression reduces to kt. The frequency should be high enough to get h nu by kt comparable to unity. For example, at room temperature where T equals to 300 K, the term h nu by kt turns out to be of the order of 1 by 5 for the value of nu equals to 10 to the power 12 Hz. Success of Planck's quantum hypothesis. The success of the Planck's distribution law based on the quantum hypothesis may be regarded as the first step to look beyond classical laws for the understanding of processes in at least some areas of physics. Now, specific heats of solids at very low temperatures. In 1906, Einstein applied Planck's hypothesis to another problem of classical physics, the theory of specific heats of solids. It is well known that atoms in solids execute oscillations about their mean positions due to thermal agitation. Each atom may therefore be regarded as a three-dimensional harmonic oscillator. The classical law of equipartition of energy demands that the mean thermal energy of such three-dimensional oscillator in equilibrium at temperature T is 3 kT per atom, or 3 RT equals to 3 nkt per gram atom, where n atoms, where n is the Avogadro's number. For 1 mole, n is 6.025 into 10 to the power 23. Thus, the mean energy of solid U equals to 3 nkt equals to 3 RT. This means The lattice contribution to molar specific heat capacity Cv is dU delta equals 3R 6 calorie per degree per mole. This classical theory predicts that the heat capacity per mole is the same for all substances at low temperature. Many solids obey this law at room temperature and above, but this prediction fails entirely at low temperatures. It is experimentally found that heat capacity approaches zero as T tends to 0, as shown in figure 1.2. This puzzling problem of classical physics was resolved by Einstein following Planck's hypothesis, assuming that a solid can be represented by a collection of harmonic oscillators which can take only discrete values n, h, nu, where n is an integer and nu is the oscillator frequency. Einstein considered the simplest model where all the oscillators have the same frequency nu 0. Thus, the internal energy of the solid is U equals to n into 3h nu 0 by exponential h nu 0 by kT minus 1. And the lattice heat capacity at constant value is Cv equals to del U del T equals to n into 3h nu 0 exponential h nu 0 by kT by exponential h nu 0 by kT minus 1 whole square into h nu 0 by kT square. This again can be expressed as Cv equals to 3nk into theta e by t whole square exponential theta e by t divided by exponential theta e by t minus 1 whole square, where theta e is h nu 0 by k is defined as the Einstein temperature. The above expression may be used to obtain the reasonable fit to the experimental data for a given material by choosing an appropriate value for Einstein temperature, which is found to be of the order of a few hundred degrees absolute. Einstein's formula is found to be in fair agreement with experiment for T much greater than theta e. But again, at low temperatures, the agreement is poor. For non-metals, the heat capacity approaches 0 as T cube, whereas Einstein's formula predicts Cv equals to 3R into theta e by t whole square exponential minus theta e by t. Debye in 1912 successfully explained the T cube variation at low temperatures by considering the presence of a spectrum of frequencies. Indeed, Einstein's derivation was by no means the last word, but it was sufficient to demonstrate the inadequacy of classical concepts, namely that material oscillators like radiation oscillators can take only discrete values in limiting situations. Photoelectric effect. The phenomenon of photoelectric effect was observed for the first time in 1887 by Heinrich Hertz, while he was carrying out experimental investigation to establish the existence of electromagnetic waves in order to confirm Maxwell's theory. He noticed that ultraviolet light falling on metallic electrodes produced high voltage sparks across the detector loop. Light shining on the metal surface facilitated to release free charge particles, which were identified as electrons. Later, this phenomena was studied in detail by W. Hallwachs and Philip Leonard. The detailed investigations carried out by Leonard revealed the following striking features, which cannot be explained by classical electromagnetic theory. Striking features of photoelectric effect. There exists a minimum called threshold frequency of the radiation characteristic of the surface below which no emission of electrons can take place. It does not matter what the intensity of incident radiation is and for how long it falls on the surface. This observation is in contradiction with the classical wave theory according to which photoelectric effect should occur for any frequency of incident radiation provided the intensity of radiation is large enough for ejecting the electrons. The maximum kinetic energy of electrons emitted by the surface is found to depend linearly on the frequency but is independent of the intensity of incident radiation. According to classical electromagnetic theory, the maximum kinetic energy of the electrons should increase with the increase in intensity but should be independent of frequency. Experimentally, the photoelectric emission is an instantaneous process without any apparent time lag. It is less than or of the order of 10 to the power minus 9 seconds. In wave picture, the absorption of energy takes place continuously. The energy absorbed per electron per unit time turns out to be small. Explicit calculations show that it can take a sufficiently long time for a single electron to pick up sufficient energy in order to come out of the metal. In 1905, Einstein proposed a radically different picture by suggesting that electromagnetic radiations only exist in discrete energy corpuscles or quanta called photons, each photon having an energy E equals to h nu, that is equal to hc by lambda. He thus advanced the idea by generalizing Planck's postulate of quantization of energy to postulate that electromagnetic radiation by itself exists in the form of light quanta. According to Einstein, when a photon falls on a metallic surface, its entire energy h nu is used to eject an electron from the atom. If h nu exceeds the amount of energy called the work function W required to escape the electron from the surface of the metal, the electrons would move out to the surface with energies up to maximum value E max equal to h nu minus W. This result was verified in series of experiments carried out using sodium and potassium as photoelectric surfaces. According to the Einstein's equations, plot of kinetic energy E max, which is experimentally observed in terms of stopping potential V0, just sufficient to stop the fastest electrons, with frequency nu of incident radiation, gives a linear fit showing that there exists a threshold frequency below which no electron emission can take place. See figure 1.3a. So figure 1.3a shows the plot of stopping potential versus frequency of incident radiation for two metals A and B. Note that the slope of the linear plot is same for different metallic surfaces. It is in fact proportional to the Planck's constant and charge of the electron. In figure 1.3b, there is a plot of photocurrent versus collector potential for different intensity radiation by having same frequency. So indeed, experimental data obtained by Millikan provided further confirmation of Einstein theory as shown in figures 1.3a and 1.3b. The Compton Effect. About 20 years later, that is in 1924, Arthur Compton discovered that when hard X-ray of shorter wavelength are scattered by atoms of an element of low atomic number such as graphite, the scattered radiation contains not only the original wavelength but also softer X-rays of longer wavelength. Compton was able to explain this phenomena of scattering by X-rays by assuming that X-rays consist of a collection of photons, each characterized by energy E and momentum P. Assuming that X-rays of wavelength lambda consist of a stream of photons of energy E equals to h nu equal to hc by lambda, Compton argued that when one of these quanta hits a free or loosely bound electron, it would recoil. As a result, it would have an energy E prime less than E. After the collision, therefore, the corresponding wavelength lambda prime greater than lambda. Based on this picture, quantitative calculation can be made using the laws of conservation of energy and momentum to estimate the increase in the wavelength of the scattered photon. Now consider an incident photon of energy E0 and momentum P0 which collides with an electron and is then scattered as shown in the figure 1.2. The figure shows that scattered photon of energy E1 and momentum P1, which is equal to E1 by C, making an angle theta, and the recoil electron of momentum P2 making an angle phi with the direction of the incident photon. In case of metals having low atomic numbers, the binding energy of the electrons in the atoms may be quite small as compared to the energy of the hard X-rays incident on the metal. We may therefore assume that the electrons to be at rest having the rest mass W0 equals to mc square, where m is the mass of the electron. However, since the recoiling electron from the collision may have velocity comparable to c, it would just be appropriate to use the relativistic relation for the velocity v of the recoiling electron. So, using the law of conservation of energy during collision, we have E0 equal to E1 plus T, where T is the kinetic energy of the recoiling electron given by T equals to mc square plus c square p2 square to the power half, that means square root, minus mc square equals to c into p0 minus p1. Now, the initial and the final moment of the photons is given by the relation p0 equals to E0 by c equals to h nu by c equals to h by lambda 0, and p1 equals to E1 by c equals to h nu 1 by c equals to h by lambda 1. And applying the law of conservation of momentum, we get P0 equals to P1 cos theta plus P2 cos phi, and 0 equals to P1 sin theta minus P2 sin phi, or P2 cos phi is P0 minus P1 cos theta, and P2 sin phi equal to P1 sin theta. Squaring and adding these two equations, we get P2 square equal to P0 square plus P1 square minus 2 P0 P1 cos theta. By using the above relations, and we rewrite our previous equation as C into P0 minus P1 plus MC square to the power whole square equal to M square C to the power 4 plus P2 square C square equals to M square C to the power 4 plus C square into P0 square plus P1 square minus 2 P0 P1 cos theta. On simplifying these equations, we get mc into h by lambda 0 minus h by lambda 1 equal to p0 into p1 1 minus cos theta equals to h square divided by lambda 0 lambda 1 into 1 minus cos theta, or lambda 1 minus lambda 0 is equal to delta lambda equals to h by mc into 1 minus cos theta equal to 2 lambda c into sin square by theta 2, where lambda c equals to h by mc is called the Compton wavelength. This equation is known as Compton equation. The Compton wavelength is in fact the wavelength shift when scattering takes place at 90° and can be experimentally observed, which can be compared with the calculated value. This is found to be in excellent agreement with the prediction of Compton's theory. The success of the theory presented above shows unambiguously the electromagnetic radiation manifests itself as a stream of corpuscle or quanta during scattering. So, students, let us summarize what we have learned in this module. In this module, we have explored the nature of electromagnetic radiation by studying some typical processes like blackbody radiation, specific heat of solids, the photoelectric effect, and Compton scattering. These processes clearly show that electromagnetic radiation manifests itself in the form of corpuscles or quanta of light. From our earlier studies, we also know that the phenomena of interference, diffraction, and polarization can only be explained on the basis of wave theory of light. It is therefore clear that electromagnetic radiation plays a dual role. It exhibits both as particles and as waves. This ability of electromagnetic radiation to behave both as waves and photons is referred to as the wave-particle duality. Thank you.